pen. And here we go. Hopefully you guys have paper out and you're taking notes on this. But the word rational, do you remember what that means? Right?
Any like whole number, not whole number, not whole number.
Okay, so whole numbers are rational numbers, but it expands beyond that. Right. Fraction, ratio. So the word itself, rational, means a ratio of integers. It's an adjective form of the word rational. Aiden, pay attention. But it means a ratio of integers. So what I like to think about this at this point now is I'm going to call them clean fractions. And they're clean fractions because they're fractions that are ratios of whole numbers. They can be positive or negative, but they cannot have infinite decimals that don't have a way to convert it into a fraction. So 1.3 repeating is good because that's really 4/3. But 1.3567 and just random assortment digits are not. Any terminating fraction decimal is good because 1.35 can be the same as 1.35 hundredths. But that's my point with this. Rational exponents, if I kind of think about 2 to the second and 2 to the third, give me a number you know is in between 2 and 3. Right here.
2.5.
Okay, 2.5. So we should actually be able to create meaning behind 2 to the 2.5. Now, you guys prefer to put 2.5. I prefer to put 5 halves. But that should actually have some meaning. And it's not just like how many times can I multiply 2 by itself? It's got to be something different, but still in between that. I think all of you would agree that this should probably hold true. Okay, so I know 2 to the 2.5 should be somewhere in between 2 squared and 2 to the third. What is 2 squared?
4.
And what is 2 to the third?
8.
It's not quite 2 to the... It's not going to be 6. I mean, the scale doesn't work that way. Did you guys, any of you guys on your front page, graph an exponential function and see it kind of do that thing?
Yeah.
It should be, but 6 is going to be close. It's going to be somewhere in there. And that's what we're kind of dealing with today, is creating meaning behind this. So as kind of creating meaning, I'm going to do like a little break here, and let's do a number that you guys might know. 49 to the 1/2. Right?
That'd be 7.
It would be 7. So what does 49 to the 1/2 mean? Square root of 49. Can I generalize and say that x to the 1/2 is equal to radical x?
Yes.
Okay. Can we generalize even more than that? Can I relate the fact that when I take the square root of x, I'm really doing the second root of x? So what would x to the 1 over n be?
X root the n.
We call it nth root. But yes, nth root of x. So some examples of that would be, what is 27 to the 1/3? 3. I want to focus on this one for just a second. 27 to the 1/3 is 3. And talk about what's really happening in this chapter. You guys are going to be taking your brains and how you think about math and expanding it beyond what you think you're doing. It's not simply about adding and subtracting anymore. It's not simply about multiplying and dividing. If there's one key theme about this entire chapter, it has to do with powers. And not just powers in terms of an exponent, but understanding what kind of a sequence of powers are. So 27 comes from powers of 3. And when you look at 27, you need to be thinking now that that is 3 to the 3rd power. You should recognize it as 3 to the 3rd power. 27, 81, 9, 3, 1, 0, or not 0, 1/3, 1/9. All of those are powers of 3. And how do I know that? What is 3 to the 1st power? 3 to the 2nd.
9.
3 to the 3rd.
27.
3 to the 4th. This is 3, 9, 27, 81. But let's keep going down. What's 3 to the 0?
1.
What's 3 to the negative 1?
1/3.
3 to the negative 2.
1/9.
And every single one of these powers is related to a number that's kind of a straight up -2, -1, 0, 1, 2. And we're going to be, in a sense, creating a function that takes numbers like this, -2, -1, 0, 1, 2, 3, 4, and translates them to numbers like this. We're not just going to do it for 3. We're not just going to do it for 4. Eventually, we're going to do it for any number, whether it's a whole number or not. And that is where the expansive part of this comes into play. I remember I told you guys a couple months ago that 1 acts as sort of a middle ground on the number line when you're talking about multiplying, dividing. How 1, which is 3 to the 0, and then you have numbers greater than 1, which is where we raise 3 to powers that make it bigger, and then numbers between like negative infinity and 0, numbers that make this really, really, really small. Did you guys notice when you graphed exponential functions that it never hit 0? It got really, really, really close, but it never hit 0. This is going to become 1/3, 1/9, 1/27, 1/81st. It's going to become a very, very tiny fraction. It's going to come infinitely close to, but never actually hit 0. This also means that we can create meaning behind this, 27 to the 2/3. Can you think about what that might be? 9. That is 9. It's 27 to the 1/3, but then squared. Raise to the second power. I know you're thinking when you raise a power and another power, you're multiplying them. That's good. This is how we're going to do this. 27 to the 1/3 we just said was 3, but then 3 squared is 9. And if I think about this, 27 to the 2/3 means I'm starting at 27. This number is 27. I'm backing up, taking the cubed root, and then I'm going forward again. And that's sort of what's happening. Actually, I should back up 3 places. So back up 1, 2, 3 places, but then go forward 1, 2 places. When I raise a power to a 1/3, I actually back up in the sequence of powers. And then when I raise it again to the second power, I move forward 2. And I end up right here. It's sort of a meaning behind what it means to raise a number to another number that's just not a straight up number. Okay, another little nuance of this has to do with the easiest way to go about this. So I want to start with 4 to the 3/2. Is that going to be bigger or smaller than 4? Yes. Can you tell that without knowing what it's going to be? What am I looking at right here to tell whether this number is going to be bigger or smaller than 4? Aid? Yeah, the 3/2 is more than 1. If it was less than 1, it would make the number smaller. And if it is 1, it makes the number itself. Okay? So, what is this number? What is 4 to the 3/2? It is 8. Be careful. Do not confuse raising with multiplying. Be really, really, really careful about that. Raising to a power is not multiplying those numbers together. It's raising. There are 2 ways to think about this number. One of them is this. I'm going to do 4 to the 1/2 and then cube it. And another way is this. I'm going to do 4, cube it, and then raise it to the 1/2. If you remember that when we raise a power to another power, the power of powers rule, if you remember what that says, it says that when we raise a power to another power, we multiply the powers. So all I'm doing is pulling them apart again, so we can deal with each part separately. What is 4 to the 1/2? 2. And 2 to the 3rd? 8. What is 4 cubed? 64. 64 to the 1/2? 8. Which of the 2 of those is slightly easier to do? Absolutely the first one. And here's why. I don't have to do this to show you that. I can do one that's even better to show this. Let's do 49 to the 3/2. Is it easier to go 49 to the 1/2 cubed? Or is it easier to go 49 cubed to the 1/2? I think all of you can agree 7 times 7 times 7 is a far easier problem to do than 49 times 49 times 49 than trying to figure out what its square root is. And yet they are the same thing. This one, both of them actually, are 7 cubed. You already know what 7 squared is. So just multiply that by another 7. If you want to multiply 49 times 7, multiply 50 times 7 and then subtract 7. 343. So here's the gist of today. B to the m over n, where m and n are integers. This is what we're looking at for the majority of today. We're dealing with raising to a rational exponent. The rule b to the m over n is equal to one of two things, and we're going to put them both down. You can say that that's equal to b to the m nth rooted, or you can say it's equal to the nth root of b to the m. And I think we agreed that this one is easier because making a number smaller before you make it bigger
Easier.
we'll leave that there. Nope, I'm going for it. I'd give you one, but you'd probably just be right back.
I just don't like to disrupt the middle of the class.
And that's so much irony there. Okay, so let's look at this a little more carefully. B to the m over n. This number m is on top. So it is what we raise by. I'm going to put raise in quotes here. And I'm also ending a sentence in a preposition, which I shouldn't do. I should say it is by what we raise, but, you know, that just sounds awkward. N is not on top. So it is what we... So what would the opposite of raise be?
Decrease.
It's true. So let's go root. We're going to say what we root by. I'm going to put a little star here. Usually, we root before we raise. Reason for that, if I take 2,500 and say, what is 2,500 to the 3 halves? I'll wait while whichever one of you wants to take 2,500 to the third power and then take its square root does that. But what's the square root of 2,500? 50. And 50 to the third power is 5 times 5 times 5. 125. And then 3 zeros. That's a lot easier to do. Now, you guys should relatively become very, very familiar with powers of big numbers. So, or powers of basic numbers, not even big numbers. So if I take 1 over, let's just do 125, and say, what is this raised to the 2/3? I will still get a subset of people telling me that that is 2 over 375. That is 1 times 2/3. That's not 1 raised to the 2/3. Your first step should be to think about what is the cubed root of 1 over 125. Take that and then square it. So what's the cubed root of 1 over 125? 1 over 5. And 1 over 5 squared is 125. So let's talk about 5 over here. Powers of 5 you guys should know. Obviously you know 5 to the first. You know 5 to the second. You should know 5 to the third. And you should know 5 to the fourth. That's about as big as you guys need to go with 5. What's 5 to the fourth? 625. 125 and so on. Those are numbers you should recognize. Just if you encounter 125 or 625, you should know that that's 5 to the third and 5 to the fourth. Don't need to go larger than that. Yes, you could do 30, what would it be, 3125, but unnecessary. Don't need to go that big with it. Just keep them to numbers that are kind of basic. You're not going to get too crazy on these. Okay, next. 25 to the 1/2 plus 81 to the 1/2 squared. What is it? 196. If you got 106, you killed puppies. We cannot distribute an exponent across addition subtraction. This is really just 5 plus 9, quantity squared, or 14 squared, which is 196. Notice how your worksheet, I made it 3 columns. So I did that because you're going to do a lot of vertical work, but you're not going to do a lot of horizontal work. Let's look at this. X to the 1/2 plus y to the 1/2 squared. First of all, you guys should know, do not put x plus y, right? We know we can't do that. Don't even be tempted to. Please tell me you didn't. Okay.
I almost did. I said it out loud.
But if it was x plus y, then this one would have been 25 plus 81. I mean, like that's not how math works. If I was really going to do this, I'd want to do this. Another case of where I'll have people put x plus y. But isn't that just x plus 2 root xy plus y? You FOIL that. So we're not going to see a lot of those kind in this chapter, but I do want you to kind of connect this back to you can never distribute an exponent across addition subtraction. Okay, let's add a complication. Let's do negative 36 to the 3/2. And right away a question's going to come up. Do I mean that the negative is being raised to the 3/2, or do I mean that it is not being raised to the 3/2? It's not. If I wanted it to be, I would do that. So we're going to put that problem right here where we create it. These are not the same thing. And this one is the same thing as this. We'll never really write it like that, but we'll think about it like that. 36 to the 3/2. Yes, Tim?
I have actually a question on 3. So you said don't distribute an exponent across addition and for subtraction. So like what we did when we got the x plus 2 plus y plus y, what was that called? That's not distributing it?
That's multiplying this by itself
Okay.
as a binomial. So the acronym we use is FOIL, but really we're just using the distributive property to multiply. This goes to this, this goes to this, this goes to this, this goes to this. If you square just the x and the y, you actually ignore that middle term. You completely ignore that. And so it's not quite right. It's why, like, when you do this, and I don't know if you guys have seen this, but if I have x and y like this, and I want to multiply that, this side would be x plus y. And if I want to multiply this by x plus y, and I call that x and y, if I do just x squared and y squared, this is x squared, this is y squared, I actually just get those two, but I miss this, which is an xy, and this, which is an xy. That's a visual of why you cannot ever distribute a square across addition subtraction, because you completely miss out on this and this. You actually only get the area of just the two little squares inside, and it's not complete. Okay, coming back on this one, what is 36 to the 3/2? Yeah, 216, with a negative would be negative 216. Square root of 36 is 6. 6 to the 3rd power is 36 times 6. Something worth noting is if I'm doing 36 to the 3/2, that's 36 to the 1.5, like that. And 1.5 is 1 plus a half, which is the same thing as 36 to the 1 times 36 to the 1/2. This is going backwards with your rules. When you multiply with the same base, you add the exponents. So I'm completely working my way backwards from there. This is 36 times 6. And that's actually what's happening when you do that. You're kind of taking, okay, so 36 to the 3/2 means I'm keeping the 36 and I'm multiplying it by another 6. Little advanced. You guys will probably just end up going back down to 6 and then raising it up again. What would this be? Right?
Wouldn't it also be negative 20?
Well, the problem with that is that we've got this thing going on.
Not possibly.
Yeah.
You just add
216 I.
Yeah. Right now we're going to say not real, and we're going to leave it like that. Part of the reason we're going to leave this as not real, and this will have eyes in it. I know you guys kind of see that. Faison, calm down. But part of this is that when we take a negative number and I raise it to a power that is not an even number or an odd number, we have a little bit of an issue. Here's what I mean. Every one of you guys knows that if I take negative 3 and raise it to an even power, what does it become? Positive. If I take a negative 3 and raise it to an odd power, what does it become? What happens if I take negative 3 and raise it to the pi power? Exactly. We don't know. We don't have a way to work with that in real numbers. In complex numbers we do, but skip ahead now about 2 more years to learn about the specifics with working with this. So right now, all of your different things that we do, all of the different problems we do, will always have pretty much positive bases. Meaning that the number that you're raising is going to be a positive number. You saw that in the worksheet on the back where we talked about b values. They were always positive. They were, whether it was between 0 and 1 or 1 and infinity, you had b values that were always positive. Okay, next problem. I'm calling this 7 because, I've already used 6. Let's do 64 to the negative 1/6. Okay, final complication really. We're going to take 64, a positive number, and we're going to raise it to a negative exponent. This is going to be 1 over 64 to the 1/6, which is 1/2. What is 64 to the negative 5/6? 1 over 64 to the 5/6, and yes, that's 1 over 32. Okay. 2 more problems. We're going to take this one and write it in exponential form. So we're just going to kind of work our way backwards and pull this out of the radical. A to the 36 thirds is 12. B to the 35 thirds. You get A to the 12th, B to the 35 thirds. And then lastly, we're going to do this, which we could not do before. And we're going to do this in radical form. So sometimes to go to radical form, you have to go back to exponential form and then work with that. We were not able to do this back with radical chapter. We can now. 3 raised to what? Times 3 raised to? When you multiply with the same base, what do you do to the exponents? What is 1/4 plus 1/5?
9/20.
Yes, 9/20. Sorry, 4th grade wants its fractions back. And then if we put this back in radical form, this is the 20th root of 3 to the 9th. 3 to the 9th is probably too large to write out right now, so this would be fine. But you actually just multiplied radicals together with different roots, or different indices, I should say. Okay, we're done for the day.